Fundamental principles of mechanics. Content to be covered. 1. Principles of Newtonian mechanics. 2. Newton's laws of motion. 3. Newton's law of gravitation. 4. Concept of weight. 5. Principle of transmissibility of force. 6. Law of parallelogram of force. The study of mechanics depends upon few fundamental principles which are based on experimental evidences. In the first, very important principle is principles of Newtonian mechanics. Sir Isaac Newton summarized, clarified, and extended Galileo's work. In addition, he has formulated the law of universal gravitation, the mathematics of calculus, and formulated the 3 laws of motion. Although these laws has been discovered experimentally by Galileo about 4 years before Newton was born, Newton was the first to systematize them. The great importance of Newton's contributions to mechanics is evidenced by the fact that classical mechanics is often called Newtonian mechanics. The theories of relativity and quantum mechanics show that Newtonian mechanics is inexact when speed reaches to speed of light or when the motion of subatomic particles is considered. However, Newtonian mechanics is extremely precise for all other cases. Let's take an overlook of these laws. Newton's first law of motion, which states that a particle continues in its state of rest or of uniform motion in a straight line unless an external unbalanced force acts on it. Newton's first law contains the principle of the equilibrium of forces, which is the main topic of concern in statics. This law is actually a consequence of the second law, and to understand the statement it is necessary to use the formula of force F obtained in second law. As per the second law of motion, force F is equal to the multiplication of mass of the body m and acceleration a. Let us see the first part of the first law, which states that a particle in rest will remain in rest if external unbalanced force not act on it. As per this statement, if body is at rest, means its acceleration is 0. So above equation become: if body is at rest, then acceleration is equal to 0. Force is equal to 0, which is the condition of static equilibrium. Second part of first law states that a particle continues in state of uniform motion in straight line remains in motion if no external force stops it. As per this part of statement, uniform motion is prime concern. As you all know, acceleration is the rate of change of velocity with respect to time, that is derivative of velocity with respect of time. But as statement suggests, velocity is uniform and derivative of uniform or constant is always 0, that is acceleration is 0. Again, it is condition of stable equilibrium. Newton's second law of motion. In Newtonian mechanics, most important law is second law, which states that the rate of change of momentum of a body is directly proportional to the force acting on it and takes place in the direction of applied force. Mathematically, force is equal to change of momentum with respect to time and can be written as force F is equal to final momentum minus initial momentum with respective time t. But momentum is equal to mass into velocity. Them above equation become force F is equal to mv minus mu divided by time t, in which v and u are final and initial velocity of the body respectively. We can write above equation as force F is equal to m into bracket v minus u divided by time t, but change of velocity with respect to time is acceleration. Equation of force can be written as force F is equal to mass m into acceleration a, where F is the resultant of forces acting on the body of mass m moving with acceleration a. This law forms the basis for most of the analysis in dynamics. Newton's third law of motion, which states that to every action, there is an equal and opposite reaction. The force of action and reaction between interacting bodies are equal in magnitude, opposite in direction and collinear. The third law is basic to our understanding of force. It states that forces always occur in pairs of equal and opposite forces. Thus, the downward force exerted on the surface by a man is accompanied by an upward force of equal magnitude exerted on man by the surface. This principle holds for all forces, variable or constant, regardless of their source, and holds at every instant of time during which the forces are applied. In the analysis of bodies under the action of forces, it is absolutely necessary to be clear about which force of each action-reaction pair is being considered. It is necessary, first of all, to isolate the body under consideration and then to consider only the one force of the pair which acts on the body. This explains the importance of free body diagram. Newton's law of gravitation. Shortly after formulating his three laws of motion, Newton postulated a law governing the gravitational attraction between any two particles. The law states that the force of attraction between any two bodies in the universe is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Mathematically, attractive force between two bodies is equal to product of universal gravitational constant g, mass of first body m1 and mass of second body m2, divide by square of distance between two bodies. Concept of weight. Let us see the concept of weight, which is derived from the Newton's law of gravitation. As per the Newton's law of gravitation, any two particles or bodies have a mutual attractive, gravitational, force acting between them. In the case of a particle located at or near the surface of the Earth, the only gravitational force having any sizable magnitude is that between the Earth and the particle. Consequently, this force, termed the weight, W, will be the only gravitational force considered in our study of mechanics. Suppose a mass of mkg is located near to the surface of the Earth. If Earth is assumed to be of uniform density and mass, then me is the mass of the Earth. Then, as per the statement of law, these two bodies with mass m and me must have force of attraction. If r is the distance between these two bodies, then mathematically we can write weight force is equal to product of universal gravitational constant, mass of body on Earth's surface and mass of Earth divided by square of distance between two bodies. Here, universal gravitation constant, mass of the Earth and distance between Earth's center and surface is assumed to be constant. W is equal to m into bracket g into me divided by r square. Compare above equation with the equation of force that obtained from second law of motion, which is force F is equal to mass m into acceleration a. By comparison, we can say that the term g into me divided by r square is synonymous to acceleration and termed it as acceleration due to gravity. So we can write g into me divided by r square is equal to g. Equation of weight can be written as W is equal to m into g. But the term acceleration due to gravity is not constant, as it depends upon the r, that is distance between any body on Earth's surface from the center of the Earth, which may vary. Principle of Transmissibility of Forces, which states that a force may be applied at any point on its given line of action without altering the resultant effects of the force external to the rigid body on which it acts. Let's understand the principle with the example of the block pushed by a man. The line of action of the push force is shown in figure. The outcome of the push force is the forward movement of the block. But what happens if the man, instead of pull the block with same force and in same line of action? Yes, outcome will be the same, that is forward motion of the block. Thus, whenever we are interested in only the resultant external effects of a force, the force may be treated as a sliding vector, and we need to specify only the magnitude, direction, and line of action of the force, and not its point of application.